So we're gonna finally do something interesting. We're gonna add a part. So you can type add here, or you can click add here on the left. So I'm gonna use all the command line commands. So I'm gonna push enter and it'll open up our PCB library. Again, just to show you guys it works, you can click add part here and it opens up the same thing. And you're gonna see our PCB library. These have been organized in what we thought were logical groupings. It may not be the most effective or efficient or meaningful, but we're trying our best and it's always changing. So you guys can feel free to explore those. What we're gonna do is we're gonna add a microcontroller. So you guys may or may not be familiar with what is listed here, but here's the Atmega 128 RFA1, a lot of interesting stuff. This is just a microcontroller. We have the Atmega 328P, which if you're not familiar, this is actually the microcontroller that's on an Arduino Uno, something that you may be familiar with. And there's also different packages. So this package may not look familiar to you if you're not familiar with the Arduino. And this package is actually the one that's not on the Arduino. The Arduino has a through-hole package. So let's actually show you guys a through-hole component. So we're gonna add an ATtiny. Here we can see the through-hole has the pads. This is what you solder to and where the pins of the device fit through. You can also see here that we actually have a 3D model of it. Some of the ones that have 3D models will be listed with 3D, and we're going to try and use just 3D models to show you guys how cool it looks when we import it into Fusion. On the left, this is our schematic. So this is what it's going to look like on the schematic when we drop it in there, the symbol. Here is what it's going to look like on the board, and when we print the device, this is what it's going to look like. And here is the 3D model. So if we export this into Fusion, we should have over the footprint of the device the 3D package. Our devices have a description. Most of them do not, but all of them will have this metadata, which I'm going to go into detail later. But I want to tell you guys that this is a very powerful way of learning as well as actually making your product. So it has the data sheet. You can click here, copy it, and then go into Google or your web browser and punch in that website, and you'll see we have the data sheet for the ATtiny. So if you're familiar or not familiar with ATtiny, you can get all the details about it here. There's also some other information, the distributor, DigiKey, the distribution link, again DigiKey here. So if you go into your web browser and punch this in, then you guys will be taken to DigiKey, where you can go ahead and find the data sheet, other very valuable information, and even add this straight to your cart and then use it in your design. And we'll show you a very easy way where you can design an entire schematic, entire board, 3D model, everything, and then you can actually export a bill of material of your entire design and just go ahead and order it on DigiKey. Then you'll notice we do bias a little bit towards DigiKey. It's just very convenient. I like their site and them as a distributor, but there's other things like Mauser, Newark, and several other that are just as great. So some of this information is very powerful and useful, as we'll show later. In this ATtiny, which you don't have to be too familiar with, it's just an AVR microcontroller just like the Arduino. Same family, just smaller device, less pins. So this one had 28, 32 pins. These ones have 8 pins. And that's how you can see here. So it's an ATtiny X5, or in this case, it's ATtiny 85. They have different variations, ATtiny 25, ATtiny 45, ATtiny 85. Again, you don't have to know about that, just to give you some background of the naming convention here. It is a DIP 8, which is dual inline package, has 8 pins. And if you click on this other one here, it's the same thing, through hole. 3D model didn't generate for some reason, but it's fine. It does have a 3D model, but this one has the connector that you can actually plug into. So a dual inline package connector in which you plug in the chip into. So this one doesn't support that. And as you can see here, it has the same data sheet, same distribution link, but also has one for the connector. So just to show you guys what I mean by that, again, we'll put it into our web browser, and this is what it is. So the actual chip itself would plug into this, and this would be soldered into the PCB, so you can reuse the chip or reprogram it or whatever you need to do with it. Cool. And some other metadata that is interesting about the connector in addition to the device. This one is a little different. If you notice, these guys were green pad. It's a through-hole component. This one is a surface mount component, and so this one doesn't go through the PCB from top layer to bottom layer. It rests on one layer, and the reason why it's red is because it's on the top layer. If you put it on the bottom layer, which you can do later, but by default all components in Eagle should be made and are made on the top layer, it'll show red, and we'll go more into the layers later, so don't worry about it too much. But here you can see surface mount, 8 pins. It actually has the same schematic symbol if you notice between all 3 variants, and this is what its 3D model looks like. Doesn't have a through hole part, but this rests on top of each of these pads. Has some metadata on it too, so you can go ahead and order this if you wanted. So let's go ahead and put a device. We're going to use the ATtinys. You don't have to know much about them, but you can look up on Google. There's a lot of information on this. We also have tutorials on ATtinys and how to use them as well. So let's go ahead and add a through hole. We'll also add some surface mount later. So when you push enter, you'll be taken to the schematic where you can drag and drop this on the screen. You'll notice that it snaps to each of the squares. So go ahead and drop it anywhere. It doesn't have to be on the origin. Doesn't matter. And you're going to notice once you click there, you can drop another one. If you need to in your design, you can drop more, but for the microcontroller, we only need one. So we'll push escape. It'll take us back to the add, and this is so that you can keep adding more components or different ones. Or if you push escape again, you'll be taken back to the interface. So we have a microcontroller. I'm not going to go into too much detail about it, but I'll give you a little rundown on the ATtiny. You're going to notice that it has these numbers here. These are the pin numbers corresponding to the device. So if we go back to the ATtiny, the way the pin numbers are labeled or numbered by convention or standard is the top left where the little dot is will be pin 1, and then it goes pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, pin 8 in a counterclockwise fashion. So here you're going to notice not in line with the footprint convention is the schematic convention, and there is no hard rules for this, but a lot of people practice this here, is that VCC is somewhere on the top. It could be on the right, but I'm putting it on the left, and then ground's on the bottom somewhere. And so you notice that it's pin 8 on the actual package, but here on the schematic it's just in the top left corner, and its name is VCC. And here ground is pin 4 on the package, but its name on the schematic is ground. And you're gonna notice other pins here. These are the ones actually on the package themselves, and it follows that counterclockwise convention, but here it may not necessarily be in that order, but it is in order by its port name. This is just the convention for microcontrollers. For LEDs and other passive components, it's not this complicated, so don't worry about it if it's kind of confusing or just sounds kind of weird or meaningless. Some of this other information is provided in the data sheet, and I listed them here. Some of it is very useful to you, some of it may be gibberish or not very useful to you in everyday design, but I'm going to go over them a little bit. So here on the right, most in the parentheses is probably the most useful to you. So you can actually program this chip like the Arduino Uno or any other Arduino device in the Arduino IDE, and when you program the Arduino, it has pins labeled, right? You know, pin 0, pin 1, A1 for analog, A2, A3, and then they have PWM pins, which are actually the same number as the digital one. You just, in your code, you use them in a PWM or in an analog fashion. So here are the actual pins where if you were to use this and program in Arduino, and there's a whole nother tutorial about that you can check out, you can actually use these pin numbers. So A0, 5, this was just to show digital, and it's pin 5. So you would use pin 5 if you want to use it as a digital pin, but you would type in A0 for your pin defines in Arduino as A0, etc. with the other ones. This other metadata is a little more confusing, but also meaningful in some other ways. MOSI is master out slave in pin. It's a digital input. It's the serial data. So this is I2C, serial data, serial clock. MOSI, MISO, serial clock, and the reset are all used. These are the serial peripheral interface. AIN is analog input. The OC0A, OC1A, and all these interesting OCs are the PWM timers, or just timers. Each of these correspond to a PWM pin, so they're PWM capable. We have the analog reference. By default, these ATtinys have a internal crystal, but you're welcome to put an external crystal as well. So that's why they have XTAL1 and XTAL2 for crystal. And these PC-ins are for interrupts. Again, most of these things you don't have to worry about, but just to show you what some of this random gibberish actually means, it does have a use, and I'm used to using some of these in some of the boards that I make. All right. So that's probably a lot more than we need to know about the microcontroller, but just to kind of demystify some of the stuff that's on this. Again, a lot of components are a lot more simple, and as you design your own boards, you'll know what you're doing, so this wouldn't be very important. So each symbol has a name and a value. So this is the name, it's MCU1. If I were to add another one and drop it in there, it would be MCU2. And then here is the value of it. So the value is ATtiny85. For an LED, it may be a color. For a resistor, it may be value. For capacitor, inductor, it'll have a value as well. But usually I put the part number or manufacturer number here. Cool. So let's go ahead and add something else a little more useful or interesting. We're going to add an LED. So we can type add here, and we're taking back to our library, and we can scroll down here or scan and find PIB LEDs, and you're going to see a bunch of different LEDs. Some of them are very intuitive, some of them are not. So here we have some IR receivers for a project I was working on. You don't need to worry about that. We have RGB LEDs that you may be familiar working with, surface mount ones, and other very interesting ones. But the ones that are probably useful to you are these LEDs, and there's a bunch of them here. I'm just going to scroll through all of them so you can see all the pictures change and all the different footprints, but if you notice, the schematic symbol across all of them stays exactly the same. But here on the right, the footprint and the 3D model may change. So here, this is a PTH for through-hole LED. This is the size. Don't worry about it. It's just the convention for LEDs. It's T134, but it's a 5mm LED. That may be more useful to you. It's a standard size. This one has no color associated with. That means the metadata here will not give you the color. But if you go to this other one, it says red, and the metadata here promises you that if you were to order this, that this will be an LED and that it will be red. Cool. Unfortunately, there's none in stock here, so I wouldn't order these, but the idea is that's where you can find it. Same with this. The metadata changes here, but notice that the 3D model and the footprint don't change along these. The only thing that changes is the metadata here, which will tell you which color you're ordering. So this is how you can, put a LED in there and it'll be red, green, or blue. Then we have the surface mount ones. So here the footprint and the 3D models change across them. So I'll scroll through them. Pretty much the sizes are changing as we go down. So to go over that a little bit, this LED is an 0402, which is a very, very tiny LED. It is 1 millimeter by half a millimeter length and width, and then the height is 0.4 millimeter. We have 0603, which are slightly larger, 1.6 millimeter by 0.8 millimeter. And again, you choose the color, blue, green. This one doesn't have a silk screen or a color. We have 0805, which is the ones we're going to use, and these are really easy to solder by hand or using the reflow method. And this one's blue. Nothing here changes except for the metadata, and this one's 2 millimeter by 1.25 millimeter. So we can scroll through those. And we even have orange and yellow as well. So let's go ahead and add an LED. Let's do an 0805 one, and we'll do blue. We're also doing it just because it has a 3D model. Some of these other ones don't have 3D models that we've associated with it yet. All right, so let's go ahead and select that. Here you see the LED schematic. If you want to rotate it, you can right click, or if you're using a trackpad, you just do a double click, and you can rotate it any way you want. And let's go ahead and drop it somewhere on the screen here. I'll put it out of the way and then show you guys another tool to move it. So we notice that it drops it. It says LED1 for the name, and the value is blue. We can go ahead and add another one, and it automatically names it to LED2, and it is the same value as well of blue. I'm going to just add 2, push escape and escape. Now let's go ahead and move these LEDs. That's why I purposely put them out of the way. You have the move tool by default. If you don't, and I usually do this because I can't guarantee that I have the move tool ready, but if you type in move in the command list or command line or click move here, you will have the move tool ready, and you'll notice that the toolbar here changes to some of the things that you can do when you move it. So if we type move, click on this origin marker here, which is hard to see. You just see it sticking out, but there's actually an origin marker right here, and this is where you can click on it to move it. So if we click here or elsewhere, it may not grab it by default, but if we click here where the origin is, then it'll highlight and we're able to move it. And so let's move it somewhere down here, and then move this other one, and we'll put it next to it, space it out a little bit so it looks nice. So every LED needs a resistor, or should have a resistor to go with it, because these pins are only capable of putting out like 20-40 milliamps. So let's go ahead and do add, and then go add a resistor. So if we go here, PIB resistors, we have the resistor library, and we'll see again several resistors. One of the things you're going to notice here is we don't have every resistor value listed, and it would be insane if we had every resistor value listed, because that means we'd have to go through and actually make every single resistor. So what we do is we've been making them as we need them. And again, one of the benefits of why we have them labeled here is because if you pick a 10K resistor that's through hole, we guarantee you that this will be a 10K resistor that is through hole. Similarly, it'll have it for surface mount components as well. So we're going to go ahead and add a resistor. We'll add a 1K resistor, and we'll add an 0805 size. It's 1/8 watt and it's 5% tolerance. Go ahead and add that, and we need to rotate it, so we'll go ahead and rotate it and line it up. You can go ahead and connect it, but I want to show you guys how to make explicit connections in just a moment. So we click add, and you click add, and then escape and escape. And one thing I want to mention is this whole resistor value thing. We don't have to have the values. Eagle doesn't care if this is a 1K resistor or a 10K resistor. It's just going to show the schematic. Same on the board. We haven't shown the board yet, but on the board it's just a pad and silk screen to show what the resistor representation is, but Eagle doesn't care that it's a 10K resistor, 1K resistor, or any value resistor, LED, or even MCU, or anything else for that matter. It's up to you, the user, to understand that this is a 1K resistor. So I can go ahead and say it's a 1K resistor, but I can put a 10K resistor or 5K or anything else in place of it. It's really up to you. But having this metadata that I keep on floating around makes it so that if you want to order all these components very easily with one single cart, without having to look up parts every single time you do a design, this makes it a lot easier for you. So I just want to show that the reason why these have values or has meaning is because we added the meaning. Eagle doesn't give you this meaning innately or naturally. All right, so let's go ahead and start connecting things. I'm going to connect them to pin 0 and pin 1, which is programming pin 0 and programming pin 1 if you're using Arduino. However, it's physical pin 5 and physical pin 6 on the actual device itself. So in order to make my connections, I like to make my boards look nice. I'm actually going to move this MCU up 1 square, and again, where I have to click to move it is this origin. So we click on the origin, I want to move it up 1, and left click again to drop it. And when we actually wire stuff on the schematic layer, it feels intuitive to use wire, which there is a tool for wire, and we see the tool options appear here. But Eagle specifically has a tool for wiring stuff in the schematic called net, which guarantees that we'll make an electrical connection. So here you can click, and if you notice that once you get to the pins of the device, that a little green dot will appear, and that's what we'll use to anchor and make our connections. So we can click here, left click, and you'll notice that it starts to bend when you move it. You can change the wire bend style. However, for the schematic, I would always use wire bend style 0, which is a right angle tool. And for the board, we'll use a 45-degree angle tool, but for schematic, always right angles. It's just convention. And then you'll notice it turns green here, and we'll make our connection with a left click. And then it'll stop us once we reach 2 terminating edges. So let's go ahead and route the rest of it. We'll connect our LED to our resistor, LED to resistor. And real quick, I'll show you guys a little hack. You can push escape to to escape the tool, type in move to switch to our move tool, and now we're in the move tool, and we can click on our resistor, which has an origin marker in the center, and we can actually connect the devices like this, and they are connected. However, I try and space out my connections so that I know for sure that they're connected. So if we move it out, we'll notice that it actually generates a net for us. So it might be a useful tool later as you get more and more familiar with Eagle. The next thing we need to do is we need to connect the grounds here together, and we could very well make our ground connections like this, except imagine you have hundreds, maybe even thousands of devices, and having this ground wire connected is going to be painful. So like in maybe some circuit classes that you've taken, we always have something to represent ground, and we do have that in Eagle. So if we type in add, we can go to PIB power symbols, and there's several power symbols here, and one of them, as you'd expect, is ground right here, and we go ahead and add that, and we could drop it in here. However, if we keep on going to the library to add stuff, it's going to take a long time to do our design, and it's totally something to do when you're not familiar with our libraries. However, as you get good at designing, you can do some more powerful commands. So you can do add, and then you can give the option of adding a ground, and if you do that, it'll look for every component that has the word GND or ground in it, and you'll notice that since we're using the PIB Eagle libraries, the only thing we have in there that's called ground is our ground reference symbol or power symbol. If you have the Eagle libraries open, you'll notice it may open up the add parts here, and it'll have some more grounds because the default Eagle library also has ground power symbols, and you can just select the PIB one or the Eagle one. But I recommend again using all the PIB Eagle libraries because we've tested them, we know they work. So you can go ahead and drop these. Again, you can connect it if you want. You can add more, but I'm going to show you guys another tool. So I'm going to push escape and escape, and you can also copy symbols. So you can just type copy in the command line, push enter, and then you can click on the origin and you can make your copy, and you can drag it there, and you can copy again, and you can drag one over here. And then we're going to go ahead and route those, or net. So type in net and make your connections to ground. And so one of the benefits of doing this is we can guarantee that all these are connected to ground. And to verify that, we can type in show GND, and it'll show all the ground connections. And one thing I want you guys to observe here is actually what the power symbol does is it names the net or the wire ground. So this net or wire is named ground, this is named ground, and this is named ground. And to show that, if you type in info in the top left corner and then click on the net itself, it'll tell you all this interesting data about how it's wired from where to where, the length of it, the angle, it's nothing very important, the width of it, style, and the name. And that's what's important. So all these are named ground. So when we get to the board, we're going to be guaranteed that all these are going to be connected to ground or show us that they're connected to ground, as we'll see soon. We can also just for funsies type in info and click on these nets, and we're going to notice it has an interesting name. It's N$3, which is Eagle's convention for default names, which is N for net, $sign is just what delimiter they have, and then 3. So this is called N$3, this is probably N$4, and one of these, this is probably 1, yeah, N$1, N$2. So you'd imagine as you add more and more nets that are not named that they would be called N$5, 6, and it goes up from there. And this is to keep things unique and to show that these are independent or not connected. Cool. So we have our MCU and we have 2 LEDs, but we need a power device. So let's go ahead and add a couple more components to power it. Let's do add, and we're going to go scroll through and let's add a battery. So we can go PIB batteries, and we have LiPo batteries. This is a holder that I made for some quadcopter drone. We have some Molex connectors, and it has several or lots of metadata to buy the crimps and the connectors and the housing, etc., etc. But we're going to go to coin cell, and again we have, this is a through hole coin cell battery. This is a surface mount that's 12.5 millimeters, and this is one that's 20 millimeters, and we have a 3D model for it. So this is a CR2032 battery. This is something that you guys have seen potentially out there in the real life. And we have the actual battery itself, which is going to be the part here. So we can look here. This will actually be the CR2032 battery. It's 3 volts and has a 225 milliamp hour capacity. And the connector for it, which is this 3D model, it'll have this connector. It's a surface mount connector, as denoted here. It has pads. This is for the negative polarity where the battery will connect to, and then the positive connects to the chassis, which connects to these 2 pins. This is the symbol for it, and again the 3D model. So we can go ahead and add our battery and drag and drop it here. Escape. I'm going to copy the ground, drag it here, connect it. I'm going to pull it out to show that it's connected using the move tool. And then we don't want this to be on all the time, so we're going to go ahead and add a switch. So let's go add a switch here. PIB switches. We want a single pole double throw, and then we have several switches, and the one we're going to want to use is this guy right here. So it's a right angle one. It'll be sticking out of our board, and here's the 3D model, and here is the symbol for it. So we can add it here. I'm going to line it up very nicely for us. Escape, and then let's connect it. connect. We only need to connect one of these to the end here, and I'm going to do this one because it's already lined up, and we have our connection. We could have made a power symbol that's 3 volts and made a connection here, and then made a connection here and wired it, but that's unnecessary for this. But if we had many more things, then it would be useful. One thing that we need to add, and this is just from the datasheet of the MCU, it's not absolutely required, but it's highly recommended, is a capacitor. Let's do add, and we're actually going to cheat this time. So when we added the power symbol, we typed ground. We could have done for the resistors here 1K. However, if we typed in this, we'll get an error that 1K is not found, and that's because there's nothing that's only called 1K in there. Add 1K and then a star. This is a wildcard, and it says anything with the word 1K in there will appear. So if we do that, you notice we're going to take it into a PIB resistor, and it has 1K, and our search results show this. So if we got rid of the search results, we would see all our libraries, and we could have gone to resistors, and we could have gone to 1K, and we could have found this, or we can do this little interesting hack, 1K star, and it takes us to the same 1K resistors, and only the 1K resistors. So that's how to add the resistor. We could have done that here. To add the capacitor, we want a 10 microfarad capacitor, so we can do 10 UF star, and it'll take us to the PIB capacitors library, and you can scroll down here. We don't want a polarized one. We want one of these guys, and here again they have different sizes, different voltage ratings, and different tolerances. Here's the schematic symbol, a footprint and 3D model, and the metadata. So let's go ahead and add this one, the 0805 one. So we have our schematic, or I mean our capacitor. We'll drop it here, escape. Let's go ahead and net this guy up, and we could just connect the grounds here, but again, I'm just going to copy the ground. I think it looks nicer like this. Connect it, and notice how when I added that ground, it showed them all connected there. I want to move over the switch. You don't have to do this, but I think it looks nice and spaced this way. And that's it. I want to do the zoom to fit tool, and it fits everything on the screen. This is why it's my favorite tool. We don't have to worry about the origin and where everything is. As it is fine. And that's the schematic that we're going to build for this tutorial. So in the next video, we're going to head and show you guys the board.